Good morning, guys. Good morning, everyone. And welcome to our second webinar from the SAIMS initiative. So today we have two guests that are working together, right? So we have Mariano Lebrero from the University of Buenos Aires and Ari Zeira, that is now at UDELAR in Uruguay. So welcome, guys. Thank you very much for accept the invitation to give a talk for us. Okay, so just a small remind, the talk's about 20 minutes, then we have 10 minutes for questions, another talk of more 20 minutes, and another 10 minutes for questions. Every question you can make in the comment section here on YouTube, and then I will put these comments on the screen, just like you'll see in a few seconds. Okay, and then the speakers will be able to answer your questions. Okay, so once again, thank you very much for everyone that's here. Thank you very much for the speakers. I will give now the voice to Mariano, who is our first speaker of the day, that will talk about introducing Leo, an electronic structure and dynamics code designed for QM, and accelerated using GPUs. So, please, Mariano.
Thank you, Rafael. As you say, I wanted to talk about Leo. That is a code we developed in the University of Buenos Aires, financed by CONICET, and a lot of people. We call it Leo because we want to be fast and accurate, as Leo Messi. So, what is Leo? Leo is a DFT code with Gaussian function software. Is thinking from the beginning and designing for QMM computation. So we focus in medium-sized system, but we want to be very fast. I wanted to talk about this soon. So we use GPUs to accelerate it. So started, what is DFT? Briefly, is a method to solve the Schrödinger equation to find the electron problem. It's based in the Kohn-Sham theorem, which shows that the density and the wave function has the same information, and they are related together, each other. So yeah, and give us a way to express the energy in terms of the density. This is the whole equation, and this term, the exchange correlation term, is the expensive one. But the principal characteristic of DFT method is has a very, very good relation with the cost and quality. It still is still very expensive, so we cannot apply any electronic structure method to a system of a big size. I mean, a protein or thousand of atoms. So for trade with this this system, we use a methodology, maybe you know about it, called QMMM, which are part of the system. We treat it with quantum mechanics using DFT, or could be another method, and the rest of the system we can treat it like molecular mechanics, like point charge and strings and things like that. In this method, we write the energy, the total energy, like a sum. There is a different approach to QMM method, but which we use is that write the energy at the sum of the QM energy, M energy, and an energy of interaction between these two systems. And we have a form to write the QMMM interaction, like part of the interaction between the MM charge with the density of the QM part, and the interaction between the nucleus of the QM part with the MM charge, and with a Lennard to avoid the superposition of the QM atoms and the MM atoms. This is a picture of the Leo solvated by some Iceland guy. Well, this is a great advance, but it still remains very expensive. For example, if you want to modulate the active site of a copper domain, a copper transport protein, COPA, name it COPA, you should use 34 QM atoms, and in the original code it takes 76 seconds per step. This is an old number I use I use them for years, so maybe today is smaller, but it's still too big. Because if you want to do something with molecular dynamics with this, like umbrella sampling or something similar, thing like that, I think Ari will talk later. You need to perform a lot of molecular dynamics with a lot of steps. So if you want to make an umbrella sample with umbrella sampler free energy profile, it will not take 800 days. So it's too much. This is what each part of the calculation consume. And we see here the major part is the exchange correlation. So we look help from computer scientists, and we accelerate our computation by the use of GPUs. I think most of you should know about the use of GPU, because all the supercomputing today use GPU, but I talked a little about it. The GPU has some good characteristic, like have a massive computer power. It's really big. It's programmable. It has an excellent relation cost power. Thank you to the gamers we pay the development of this. But this massive computer power is not too easy or a piece of cake or something like that to use, because you have to use a proprietary programming language to get the best, called CUDA. There is some issue bottleneck for the computation, like low data transfer rates between the memory of the CPU and the GPU. And more important than improved performance is very tricky. You have to manage very wisely the use of the memory, the transfers from the global memory of the GPU to the work memory and something like that. You have to change it. In fact, we should change completely the way we do the calculation to have a good performance in GPU. It has a very good performance in single precision, and in double precision is not so good. But so you should deal with this stuff. And the technology change too fast. So every years or every 2 years change the capabilities. That is good, but it's a lot of work all the time. So using a GPU with a lot of work and help from computer scientists, we can change some part of the calculation to GPU, and in several steps. I show you only two, but in several steps we port all the computation, or at least the demanding computation to the GPU. So these 800 days changed to 35 days. So this we cannot use change to you can use it. But Leo do a lot of more, and more recently we are putting on them something about with real-time DFT, time-dependent DFT, with real-time and linear response. Time-dependent DFT is deal with the time-dependent Schrödinger equation. There is a very similar theorem that the Kohn-Sham, the Colin-Runge-Gross theorem, which relate the density as a function of time with the wave function as a function of time. And we have the Liouville-von-Neumann equation that allow us to model the change on the density upon time. And we have two approach to resolve this equation. We can use a numerical solution, similar to Verlet, to see in real time the evolution of density. Or we can use some analytical solution and get information from the excited states and so on. So Leo today can perform both of these, so has a lot of power. And the QMM model has a MM part, but we tercerize this. Leo works as a library, so you can call Leo to, if you give Leo the information about the QM system and the MM charge, Leo gives you energy, forces, and what you need. So the MM part, we can use the program we most use is Amber. It has integrated since Amber 16. We use a lot. We made also a link with Gromax is tested, but we use less. And we have our own MM program called Hybrid. Has a less functionality, but we can manage and have some interesting develop. You can see maybe another talk. We can talk about Hybrid. I'm not responsible for it, but it's very intense. Oh, okay. What can we do with Leo? So in principle, what we start to do is some free energy calculation on reaction in solvent. Here I don't show the solvent, but this is a reaction that we made, in fact, for Ari, who is talking next. Not about this, so I can show you. This is a reaction with hydrogen peroxide and cysteine. It's a very important reaction in the detoxification of peroxide in vivo. So we start studying this, and we can have the free energy in terms of reaction coordinate, but we have some. The nice part of it is that we can have some microscopical information. So we can find the transition state, and we can characterize. For example, here is the charge of distinct different atoms upon against the reaction coordinate. So we can see, for example, the transition state, the characteristic of the transition state in terms of charge. But we can see even more, and we can see we can characterize the solvation of reaction complex, the transition state, and the products. So we can see here for example, the radial distribution functions for the reactives, for the transition state, and for the products. And we can see the solvation in these three stages. We can see time-dependent properties with solvent effects. That is the MM part. For example, we can see the shift of formamida spectrum in vacuum and in aqueous solution, and we can see, for example, we can predict the shift is really similar to the experimental one. So we have a good agreement with the experiment with this, and there is another a lot of examples here are someone that we use to validate our approach. So we can see that the values of the maximum absorbing frequencies is like the same that the experimental, reproduce very well the experimental results. Well, we can do also very nice movies. Here I will show you a carotene molecule excited by a laser, but a oscillant electric field in a right frequency. In the color red or blue, there is changes on the density in the space. There are positive changes or negative changes. Oh, come on. So this is a very nice picture. So you can see this is the lowest energy frequency. So it's a very conjugated system. So it's a collective mode that involves all the molecule. Okay. Well, with real-time scheme, we can also calculate electron transfer problems. This is not my field, but you can do this with Leo. You can see the dynamic wise is like a potential put in the extreme of this molecule, and you can measure the current fluid. Also, this is a work in process. It's not published yet, but you can see we can compute the emission spectra. For example, this is an example of indole. We made a molecular dynamics, QMMM molecular dynamics on the first excited state of indole, and we can compute the probability of emission and the energy. So you can have a emission spectra of indole in different solvents. This reproduces really good the experimental results, not only in the frequency, even in the form. When you have a very broad band, experimentally see the same. And even more, we can quantitatively predict the quantum shield of fluorescence, quantum shield of indole in different solvent, which is very, very interesting because we plan to use this with tryptophan in protein that is really very used to see change in conformation of proteins, things like that. We also can do photochemistry with calling Ehrenfest dynamic, in which the nucleus and electron can move together. So you can excite the diacetyl molecule that is photoactivated reactive that produce carbene. In the excited state is very, very low molecule, but we can do a simultaneous dynamic of electron and nucleus to obtain and characterize this reaction. In summary, LEO is a DFT with Gaussian Bassett set. We have only up to the function because the function or angular moment 2 because por favor, to the function because we have to write with very careful of the subroutine, so we go to bigger angular function is complicated. It's very optimized for PBE functional. This is a functional of DFT. We can use another one, but PBE works very fast because it's what was really optimizing. We have the DFT in real-time linear response, and it's designed for QML. We have 2 flavors in the repository of our program that anyone can use. It's free and GPL version, so you can use and you can modify, and we are happy if someone do that. We have a stable version and develop. In the stable version, we have real-time DFT. Also, I don't talk about, but we have implemented the effective potential for electron near to the nuclei, electron field, ghost atom center potential, DFT tie binding also, electron transport, and Ehrenfest dynamics. And we have in the develop mode, we have a more functional, almost all DFT functional, even the hybrid one. We are linking with libint and live-exchange libraries that we don't write these publics. But this allows us to compute almost all functional, but has a cost in performance because neither of these two are accelerating GPU. We have the effective potential for forces and much more things. This is the code we are working all the time, so it has a lot of new characteristics. So I don't know how to go the times. I think it's perfect, almost. Well, this is some people that. No, there is many people that work in this code. Sorry, my daughter want to be in camera, but I don't allow that. Chemical, we have a lot of people who works in this program. Some of them, but sure, I forgot someone, so I don't want to talk about everyone. But this work start with Dario Strin, who write the first part of the code in the past century. Damian Sherlis, Uriel Borsar. Okay, so a lot of people, and we work also with computer scientists to help us overall with write a better code and in GPU overall. So Esteban Moscos is what is the computer scientist who help a lot with that. And more details, if you wanna see Leo in person, you can go to it's a repository, it's a copy in GitHub. You can make your own fork or ask for contribution. We are, as tell you before, we are happy if anyone wants to put your ideas or your crazy ideas on Leo. And the institution we pay of all of this is the CONICET and the Universidad de Buenos Aires, the Faculty of Ciencias Exactas. Okay, thank you very much. I don't know if I'm talking alone or there are people in the other side.
So,
it's very rare.
Thank you very much, Mariano. Yeah, well, actually, at least I heard everything. So I hope that other people also heard. So really nice talk. Really nice to see this kind of. You see, it's a great work, and it's been doing here in South America. So it's some really hard work. So we have a question from Pilar. You can see this. Yeah, you can see this on your screen.
Yeah, you have in quantum chemistry use of single precision is very difficult. You have to use with careful. Yes, it's a little more error, but we never use all in single precision. In the better case, we use the single precision for some intermediate calculation. For example, the exchange correlation is calculated over a grid, a very, very, very big grid points in the space. So each point in the space is calculated with single precision, but the sum of them is in double precision. So we never use all single precision. We use or hybrid precision with some computation in single and other in double always. And in fact, this has a little more error or loss in accuracy, but it is much less than 1 kilocalorie. So it's smaller than the DFT error. But yes, it's a good question.
Okay, great, guys. So I don't know if you have any other questions. So I believe that you can just leave your questions if you have the comments. So we can already, I'll just look the watch, almost 10:30. So actually I have a small question. I'm not exactly a bio stuff guy, more from water and water mixtures. And I was thinking that you actually, which is the water model that you use in the classical part of your simulation? Like SPCE?
We use different water model. You can use anything you want. The ones I like more is Tip4P because, but it works well with anyone.
Okay.
You can use anything they are in. For example, in number, its parameters are in number or something you can use, and you use. For sure, you use Tip3P and Tip4P. SPC, I don't remember, but I think yes, because for some we should use for some calculation with more flexible water we should use. I don't remember when, but yes, we use, and it works fine.
Yeah, okay, no, great. So later we can talk about a problem that I'm facing. Perhaps we can start something together.
Yeah.
Yeah.
Pantano has a question.
Sergio De Chesca.
Sergio. Yeah, no, in Amber it's not the Leo code, but in Amber has a subroutine that link with Leo. You should download the Leo apart. It doesn't come with Amber, but it is has a link to Sander. So you have to reconfigure your Amber with the Leo label, and Amber should find the Leo libraries and use it. Is in the GitHub is a explanation. Oh, hi, Sebastian.
Sorry, guys. Can you hear me? Okay, I have lost my connection. Sorry.
Okay.
Just some questions from Sebastian.
No, I know. I don't. Okay, the question is if I see the stabilization of. We see a high charge transfer. I don't know exactly what you are thinking about, but we actually see that the excited state change the order states. Yeah, the stabilization of the charge. For example, in indole molecule, which the excited state in water is one, and in non-polar solvent is a different one. We can see this. It's a paper we are finishing with Gonzalo Díaz Mirón. This is an experimental fact. No, we don't, Sebastian, we don't study this kind of system, but we happy to try it if you want, if you have one example.
Okay, so I will say thank you again to Mariano. I will now just include our next speaker and say see you soon, Mariano. I'll put you on the background.
Okay.
Okay, so our next speaker is Ari Zeira from Universidad de la República from Uruguay, and he will talk for us a little bit from his simulations using DIO. So please welcome Ari. Is all yours.
Okay, thank you. Good morning, everyone. Hope you are listening and seeing this okay. So thank you for inviting me for this webinar, and mostly thank you for putting together this SAIMS initiative. I'm very glad to be a part of it, and thank you for inviting me to this second webinar. So today I will talk about methionine sulfoxide reductases, but I will introduce these enzymes to you in a minute. But first, let me introduce myself a little bit for those of you that doesn't know me. I'm from Uruguay. I've always loved these kind of maps. I don't know if I can use the pointer. Yeah, I've always loved this kind of maps where the country borders are not shown, but we can see how the rivers and water courses connected us. I've always loved this since I was a child, and my story is a Rio de la Plata story. You know, I was born in Maldonado, here in the southeast of Uruguay, where Punta del Este is. I don't know if you know the city, and then I moved to Montevideo to study biochemistry, and then I moved to Buenos Aires to Darío Strin's lab to do my PhD and a postdoc there, always looking at the Rio de la Plata. This is very nice for me. And now I'm back. 3 years ago, I'm back in Montevideo, but I'm kind of in a dynamic equilibrium between Montevideo and Buenos Aires. The equilibrium now is pretty shifted to Montevideo due to the pandemic situation, but I'm hoping to restart visiting Buenos Aires more often. So now in Montevideo, I'm working at the SAIMS, which is the Center for Biomedical Research. It's a pretty large laboratory in the School of Medicine, the biochemistry department of the School of Medicine in Uruguay. We are there trying to start a biomolecular modeling unit there. So, and the aim for this unit is to integrate a lot of very nice experimental information that they developed there at the SAIMS, with a lot of researchers working on redox-related problems, in particular proteins. So there we have worked a lot on some solution chemistry problems. We have worked a little bit on peroxyredoxins, in particular for Mycobacterium tuberculosis. We are very interested in Mycobacterium tuberculosis. We have recently written this extensive review about this, if you want to read a little bit about peroxyredoxins. And also, a couple of years ago, we have started a very nice collaboration with a group of Karina Alieva's lab at the Pharmacy and Biochemistry Faculty of the University of Buenos Aires, regarding these very nice transporters that are aquaporins, and the possibility that they somehow transport some small molecules but related to redox stuff in the cell. But today I decided to talk about methionine sulfoxyl reductases. That is a kind of new line of research that we have in the laboratory. I wanted to share it with you as an example of how to use Leo coupled with Amber. So that's why we did go in a tandem fashion with Nano. So he explained a lot about Leo, and I'm going to show you a very specific example of how to use it. And this is the work of Santiago Sastre, who is here, and I don't know, he's kind of reciting Hamlet's speech to a cup of ice cream. I don't know what he's doing, but he's a very good guy, and he's working a lot on methionine sulfoxyl reductases. So I'm going to try to show you his work here today. So for those of you that aren't familiar with redox stuff, cysteine, tryptophan, and methionine are the amino acids most susceptible or sensitive to oxidation. In particular, methionine gets oxidated by different cellular oxidants, and the oxidation of methionine yields a racemic mist of two epimers of what we call methionine sulfoxide, the S epimer and the R epimer. And this reaction in solution would be irreversible, but in our cells or every organism present at least these two enzymes, methionine sulfoxyl reductase A and methionine sulfoxyl reductase B. There are other reductases present in different organisms, but these two are the responsible of reducing the methionine sulfoxide back to methionine, because this is a very important redox-related issue, because the oxidation of methionine in protein may lead to misfunction of proteins, to degradation of protein, and certain diseases are somehow related with the oxidation of particular methionine residues. Okay, so we as I told you before, we are very interested in Mycobacterium tuberculosis, and in particular in what we call the interface between the host and the pathogen. In that sense, Mycobacterium tuberculosis is phagocytated by macrophages mostly, and lives inside macrophages, where a lot of oxidants are being produced in order to kill the bacteria. And so the antioxidant systems from Mycobacterium tuberculosis are really important because they somehow explain how this bacteria can live and outlive us even in ourselves. So Mycobacterium tuberculosis present both these enzymes, methionine sulfoxide reductase A and B, and we are working with the two genes. We are producing the protein. We are doing some experiments. But today I'm going to talk to you about more about MSRA, which is the topic of Santiago's thesis. So I'm going to focus on MSRA only. If you have some questions about the other, I can we can discuss it later. So this is only to show you a very nice tool that we have to evaluate the reductase activity in a cellular context. So these are delta 5 E. coli cells that they are knockout for every methionine sulfoxide reductases that E. coli have, and also they are auxotrophic for methionine. So if you don't feed this bacteria methionine, they can't grow. Okay, and also if you feed them with methionine sulfoxide, they also won't grow, as you can see here, because they don't have reductases to reduce back the sulfoxide to methionine and use it to grow. So then you can complement your bacteria with some genes, with some reductases gene, in order to see if they are working or not. Okay, so here you can see if you complement this bacteria, delta 5 E. coli bacteria, with E. coli MSRA, they can grow. With E. coli MSRB, they can grow. But also if you can complement this bacteria with Mycobacterium tuberculosis gene, and also you can see here that these genes are working, these proteins are working, reducing back methionine sulfoxide to methionine and letting the bacteria to grow. Okay, and you can see it here. We use this kind of tool to corroborate that the cysteine residues that are the catalytic cysteine residues, I'm going to show you this in a minute, are really they are determinant in the activity of the protein. If we mutate any one of these cysteines here, you can see there's no growth of bacteria at all. Okay, so no more experiments. Let's go to the theoretical part, because we are at the SAIMS webinar. The methionine sulfoxide reductases present a very highly conserved active site. The topology of the active site is somehow shaped by the two catalytic cysteine residues. This one is the nucleophilic one, and this is one
You muted, Rafael.
Yeah. Okay, nothing. Yeah,
Ari
I believe
lost.
that we have a internet problem. Yeah, let's wait to see if Ari will return. Yeah. So problems from the pandemic period. Okay, so we have some minutes. I don't know if Nando want to talk a little bit more or speak anything.
You can ask some question.
Yeah. So let's wait a few minutes to see if or when Ari will return.
I'll try to write to Ari.
Yeah.
I don't have his new number.
Yeah, we're having this problem here also.
Y que yo hablé primero con ella, así que después, claro, el turno me dijo, sí, el contacto con Ana Cristina, y después ya tengo un contacto con ella, que es ella la zona, que no sabíamos quién era, pero me dijo, pero primero hablemos. Así que la voy a llamar para que nos cuente un poco por eso. Así que, si te parecía,
Okay, apparently you don't have any other question. As I say, let's wait 3 or 4 minutes to see if Ari will return or if he will answer the questions. Oh, yeah, and if anyone in the look in the seminar have the WhatsApp or the telephone, please call him.
Yes, because maybe he's still speaking to nobody.
Yeah.
I don't know
Yeah.
if you know.
Yeah, the possibility. No, but probably he's not seeing the StreamYard anymore. So yeah, at least this is a huge problem here when I'm teaching in the class, and then everything just stopped working.
The WhatsApp message don't works also. So I think he don't have just all the connection, I think.
Yeah.
Bad time.
Yeah, this happens. No, he is back again.
I don't know.
Hi.
Sorry.
Hi.
I don't know what happened.
No problem.
So where did I left?
You are talking about if you can share your screen again so we can put the stream.
Yeah.
You are just
for the start with
just start the theoretical stuff.
Sorry, kind of here.
Yeah.
No.
Yes. There.
Yeah.
Yeah.
Okay.
Yeah. Yes, sir. Yeah.
Okay.
No problem. This happens.
Okay. Are we live again?
Yeah. You are live.
Okay. Sorry,
I
guys. Sorry, I didn't know what happened. My connection went down. So sorry. So I was talking about the conservation of the active site. So I'm gonna try to go quickly on this. The biochemical catalytic mechanism is conserved also for all the species. The electron flux goes from NADPH through the thyroredoxin reductase system to the methionine sulfoxide reductases in order to reduce the sulfoxide to methionine. But the thing is that what is not really well known is the catalytic mechanism inside the active site of the reductases. So what we know from the experiments is a sulfonic acid is being formed after the nucleophilic attack of the cysteine to the methionine sulfoxide. This we know from experiments, and also we know that this oxygen atom comes from the solvent and not from the sulfoxide. So there's have to be some water attack during the catalytic mechanism. But this is kind of the current view of the catalytic mechanism, mostly coming from theoretical approaches. The catalytic mechanism goes like this. From this hypothesis, after the Michaelis complex formation, a sulfur intermediate will be formed. That it would be this hypervalent species on this sulfur, and then it goes to what they call the sulfonium cation intermediate, and then a water attack here would lead to the sulfonic acid intermediate. So as we have the crystal structure of the MSRA, we decided to start from scratch because a little bit of controversy was present in the literature about the catalytic mechanism. So start a pretty large, extensive the molecular dynamics on different states of the protein, the free protein, the Michaelis complex, different protonation states of the important residues at the active site, mainly this cysteine residue, which is the catalytic cysteine residue, which has to be in the thiolate form, in the anionic form to react, but also in the we test the different state of protonation for this glutamic acid. As I told you before, this glutamic acid needs to be protonated in the natural form in order to deliver a proton to the sulfoxyl moiety. So we, by constant pH molecular dynamics, we kind of corroborate that this glutamic acid, let's say, have an anomalous pKa. Okay, you can see it here. But the most important thing is after the Michaelis complex gets formed, this pKa shifts to the right a lot. So we are kind of confident that this glutamic acid would be in the neutral form when the reaction occurs. So then we decided to study this first step using a multi-scale approach. We test this by electronic structure calculation and model system. Also, we test that we kind of reproduce what was published in the literature using the onion mechanism formalism, but we try to scale up this and to use LEO as Nano told you before, because with LEO we can do free energy profile determination at room temperature, let's say, because we can do some sampling, like umbrella sampling that we choose to use here, and take into account the entropic, the temperature effects. So we kind of did that, and after a little work, we ended up with this nice curve here that you can see the free energy as a function of the reaction coordinate. Here the reaction coordinate is somehow easy, is the combination of this distance and this distance. This bond is kind of making through the reaction, and this bond is desaturating through the reaction. But you can see here that this process needs to be coupled with two proton transfers. I will go again. The first proton transfer goes from the glutamic acid that I did show you before, and then a second proton transfer from a tyrosine nearby needs to be accomplished in order to get to the product that would be a water molecule. You will see it here, and the species that we call the sulfonium cation. Okay, so this is this was all performed in Leo Amber. They would take kind of 1,500 GPU hours. It's not a lot, but it's kind of computationally cost. So computationally expensive. So another thing that I want to show you here is that the sulfuran species that would be something like here, a species that would be something like here, we didn't found that species as an intermediate. Okay, it was proposed that it was a reaction intermediate, and it isn't from our simulations. We are hypothesizing that it's only like a rugosity in the CEP, in the potential energy surface, that once you sample the reaction, taking into account the temperature effects, you lose this rugosity, and then you didn't see, we cannot see the sulfuran as an intermediate. Okay, so we also try this in order to somehow assess to the importance of this glutamic acid. We make some mutants of the glutamic 52. You can see it here, and you can see there's not growth of bacteria. This is our experiment as I showed you before. So that glutamic acid is really, really important for the activity of the enzyme. Okay, and this is a kind of take a home message about, I know all of us know this, conformation and solvation matters. Okay, this is kind of obvious, kind of trivial, but this is an example of how we can do the things wrong. If you only take into account the crystal structure and only, I don't know, you can equilibrate and thermalize your protein before you do the free energy calculation, you will get this curve. Okay, really, 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 really wrong picture of the energetics of the reaction, and in this case is somehow related with how is the cysteine and the sulfoxide solvated in the initial somehow initial conformation. Okay, so I know we all know about this, but we also see a lot of works in the literature that they do some onion stuff after coming only from the crystal structure or only from an equilibrated somehow structure. So we think it's very important to before doing some reactivity studies, you have to know a lot about the dynamics of your system. So this is only to share with you some troubles that we have when we try to do this kind of computational expensive free energy determinations. Okay, so then we go to the second step. We did go to the second step, and first we kind of describe the dynamical behavior of this intermediate, the product of the first step, that would be the sulfonium cation, and this is really important because a water molecule needs to attack here at this cysteine that is forming this kind of disulfide bond here, but we need a base here because the sulfonic acid would form an OH moiety here, but a proton needs a base to get the proton here, and we kind of found this nearby the cysteine residue that somehow we scale up to describe this second step by again using some electronic structure calculation, using the onion formalism, but scaling up to the case, when we to do this with only one reaction coordinate, we have a lot of problems, and then we have to sample the path, the reaction path, using two reaction coordinates. This is a 2D free energy map. Okay, so you can see here that in the transition state of the reaction, bond is associating and liberating the free methionine here. I don't know why the video is not playing again. Can you see it here? I don't know. Okay, there's no problem. You can see that in the transition state of the reaction, when this bond is forming, the proton transfer to the histidine residue is, so that's really a very nice result, because we didn't have to, we have to couple this proton transfer in order to sample correctly this reaction path of the second step of the reaction. Okay, so then in order to finish, we wonder if this histidine residue is conserved, and then this is our primarily preliminary bioinformatic studies, and we kind of found that this histidine residue is conserved, very conserved in eubacteria, particularly in pathogens like in Mycobacterium tuberculosis, but is not conserved in eukaryota, in other mammals, or also in prokaryota. And so we are trying to find if this how this second step would be universally in terms of the chemistry that is occurring at the active site. 4 of the 10 non-reductant reductases that are deposited in the PDB present a histidine residue well oriented to do this kind of show, but maybe other reductases uses or water as a base, or another residues that we don't know as a base. This is a very ongoing project that we are trying to understand this stage of the reaction. Okay, so in order to finish these partial conclusions and perspective, that we didn't found evidence for the sulfuran as an intermediate of the reaction, so this would not be an intermediate. And then we also show that we need some acid-base catalysis coupled to the second part of the reaction in order to get to the sulfinic acid. And now we are trying to work on the constructing the last part of the reaction, that would be the attack of the cysteine residue, the resolutive residue, to the sulfinic acid to form here a disulfide form. This is will be in the next webinar. I hope we have this solved. In the people, in particular Santiago, this is the work of Santiago, but also people from Dario's lab Dario Strin's lab is involved. Dario and Jonathan also, Bruno Manta, Madi, and Rafael here in SAIMS, in the SAIMS lab, are working a lot with this kind of enzyme. And also I wanna thank the people and the institution that somehow sponsor this project. Okay, so thank you very much to all of you. Rafael? We cannot see the sulfuran as an intermediate. Okay, so we also tried this in order to somehow trying this in order to somehow. I'm not listening, Rafael. Sorry.
Oh, sorry, I was muted. Sorry, guys. So here's the first question from Sergio.
Okay, sorry about the connection problem. I didn't know what happened.
No problem. I'm also having problems with connection today. This happens.
Okay. I see there the Sergio's question. That's a really good question. In this case, it was not easy. You can saw there we did perform the free energy profile from the not good conformation, from the wrong conformation. I don't know. I would advise to do a very good exploration of very good sampling of the dynamics of the Michaelis complex if you are simulating an enzymatic reaction, and then try to visualize if some conformation that comes from the MD are somehow better poses or better adjusted to the reaction that you are going to do. Sometimes you need to do a little bit of QMMM sampling in order to visualize that conformation is not a good one. Okay, it's not an easy task.
Okay, great. So I don't know if you have any other question from the audience. Meanwhile, we already have one researcher for our next webinar. So Fernando from Universidad Andrés Bello from Chile proposed a talk about his work in COVID-19. So we have one more slot for the next month. So if you want to give a talk, you just send me an email. And also I believe that it will be nice if you have another work on COVID-19. So we can make, just like this week, we have two researchers work on the same area, in the same stuff. Then we can have for the next month also researchers talking, working together or talking about the same topic. So just to finalize, I want to thank you very much for our both speakers from today. Okay, it was really, really nice talk. Just remember also that all the video will be available in our YouTube channel, and even with the connection problem that we had today, this will happen in the next month or probably years, since this pandemic time will last a few months at least. So thank you, guys. If you want to say anything, please feel free.
Okay, no, thank you for the invitation.
Yeah, thank you very much.
Everyone for being there.
Okay, guys. So see you in the first Monday of October. Have a nice week, and take care of yourself. Stay home and wash your hands. Bye, guys.